Thank you very much. And, well, thanks a lot for the invitation, for opportunity to spend some time here in Rimini. And yeah, so this talk is very much going to be in the same direction as Nicola's talk. But the method is going to be completely different. And so in particular, there's the class of systems that we can treat is different. So there's a non-zero intersection, but it's sort of maybe not such a big intersection actually between the class of models that the two techniques can treat. So the goal is to try to understand this sort of weak universality. So probably most of you, of course, know what I'm talking about. So let me just remind you, maybe for some of the members of the audience who are not so much part of this business, or maybe some of the younger members of the audience. So essentially, there are two natural universality classes for interface fluctuation models. Okay, so you look at any kind of situation where you have a one-dimensional interface that somehow separates two phases, and you're interested in studying the fluctuations of that interface. And the two universality classes are first the Edwards-Wilkinson and Edwards-Wilkinson universality class, if you want, corresponds to symmetric interface fluctuations. Okay, so you see this, well, if you look at the height function for the symmetric simple exclusion process, for example, but you would also expect it, for example, to see these kind of fluctuations for like the 2D Ising model below the critical temperature and zero magnetic field, where you have complete symmetry between the plus phase and the minus phase. And you start with an initial condition that has sort of pluses here and minuses here, and you want to look at the fluctuation of the interface between the two. You would also expect this to be in the Edwards-Wilkinson. And so here the fluctuations are actually just Gaussian, and they are given by the stochastic heat equation. So it's just dTh equal Laplacian h plus xi, and xi is space-time white noise. Okay, so if you want the expectation of xi of xt, xi of ys is delta t minus s, delta x minus y formally. Okay, and this, of course, you know everything you want to know about it. And the second universality class is, of course, the KPZ universality class, which this conference is about. And this corresponds to non-symmetric interface fluctuations. Okay, so think of, for example, well, if you take still the 2D Ising model, well, think of applying an external magnetic field, and now suddenly one of the two phases becomes more stable than the other one, and then the stable one wants to go and invade the unstable one, and in that case, you expect to be in this KPZ universality class. And well, here, we don't have an equation that somehow describes the large-scale behavior. So, well, it's very recently, since we heard in Konstantin's talk on Monday or something, I think it was, or Tuesday, that now we have a characterization of the scaling limit, full characterization of that scaling limit. It doesn't really satisfy an equation. The closest it comes to satisfying an equation is you would, in some sense, want to write down this equation here. That's the closest it comes to satisfying an equation. But of course, this equation has viscosity solutions, and then solutions are deterministic, whereas this object is not deterministic. Okay, so it's still a Markov process, it's a random object. In some sense, you can view it as there is a sort of Lax-Olenek type characterization, which looks similar to the characterization of the viscosity solutions to the equation, but there's an additional noise term. So there's some sort of plus noise here, but you can't really write an equation for it. And now, so each of these universality classes, of course, has their sort of basins of attraction, if you want, in the sense that if you take, your favorite model, like symmetric simple exclusion, for example, and then you start to look at larger and larger scales, then the picture that people have is that when you zoom out, you see different models at different scales. It's of course the same model but rescaled, but if you look at just observables measuring things at scales of order 1, they will of course take different values, and these will converge to what you see for Edwards-Wilkinson. And then you have other models, like ASAP, for example, where if you rescale, you converge to this KPZ fixed point. And now, what does the KPZ equation, what role does the KPZ equation play in this model? So the KPZ equation, it's sort of the equation that kind of interpolates between these two. Okay, so formally, it's the equation dth equal dx square h plus dxh square plus psi, again with space-time white noise. And this equation itself is not, so these are renormalization fixed point. They are scaling limits, and so they are in particular scale invariant, right? And they are scale invariant under different scalings. Okay, so this guy is scale invariant under the scaling lambda h x over lambda square t over lambda 4, in the sense that if you look at this function here and you plug it into this equation, it satisfies exactly the same equation again. This guy is invariant under lambda h x to lambda square t over lambda cube, in the sense that if you take this guy and you plug it into this equation, you get exactly the same equation back. Okay? And therefore, of course, this equation here is not invariant under any of these two scalings. But what happens is that if you rescale this equation under this scaling and you look and you zoom in, so you look at what happens at small scales, then formally, this term disappears. So this term ends up with the whatever power of lambda that it picks up, which is such that when you zoom in, it formally goes to 0. Whereas if you rescale this equation with this KPZ scaling and you zoom out, okay, then formally what you see is that these two terms disappear and only this term here survives. Okay? And so the KPZ equation, if you want, is a line that sort of connects these two. And so this is a model which has the property that if you zoom in, meaning going sort of backwards in these arrows, since the direction of the arrow is zooming out, okay, so if you zoom in, it moves back to the Edwards-Wilkinson fixed point, and if you zoom out, you move to the KPZ fixed point. Okay? And now the weak universality of the KPZ equation, if you want, relates to the fact that it's the conjecture that it's the only model that has this property. Okay, so the KPZ equation is supposed to be basically the only process which has the property that on the one hand it's in the KPZ universality class, in the sense that when you zoom out and at large scales you see KPZ fixed point, and on the other hand when you zoom in, you're in Edwards-Wilkinson universality class. So at very small scales you just see the stochastic heat equation, okay? And so now how do you want to probe this? So of course this isn't, when what I just said, I said it's a conjecture, but it's not really a mathematical conjecture, right? I didn't give you a mathematical statement. It's not at all clear what a rigorous mathematical statement of this would be, right? Because there's no decent space of all interface fluctuation models or anything like that, right? So one way of probing this is the following. Right, so if you look at this picture, it sort of looks very much like, well, of course, this two-dimensional thing is very suggestive, but you think of it as being in some kind of infinite dimensional space, but it still looks like here you have something like a dynamical system, and you have a fixed point, and you have a stable manifold, and you have an unstable manifold. And in some sense, this weak universality conjecture says that the unstable manifold is of dimension 1. And so how do you go to the unstable manifold of something? Well, what you do is you start off from somewhere which is very near the stable manifold, okay? And then you follow it. And then what's going to happen, right? So if you start from somewhere here near the stable manifold, and you follow it, then what you expect is that you see something which does something like this, right? So it kind of starts to follow this. It wants to flow into this Edwards-Wilkinson fixed point, but then you actually weren't quite on the basin of attraction of that fixed point, and so eventually it bifurcates, and you flow into the KPZ fixed point. And now if you look at, if you let this little interval here go to 0, and you look here at the correct scale, well, then you should pick up something on this heteroclinic orbit, if you want, okay? And so another way of stating this is basically you take any model which is in the Edwards-Wilkinson universality class, you do a small perturbation of it, which destroys the symmetry of the model, and then generically, you're going to end up in the KPZ universality class, and then if you make this perturbation which destroys the symmetry small, and you scale out at the correct scale, then you're supposed to see the KPZ equation. Okay, that's basically what it says. So, okay, so what we do is we start from essentially the simplest kind of models that you have in the Edwards-Wilkinson universality class. So simplest model in Edwards-Wilkinson, which is simply take a, say, call it DTH0. So you start with essentially the same equation, but you replace white noise by, basically any sort of reasonably nice stationary process which is sufficiently mixing. And here we're going to make our life even easier, so we're just going to assume that this guy is just some Gaussian process with covariance rho, which is smooth, and integral of rho equal 1. And I'm going to even assume that it's compactly supported. That's not very important. Okay, so you just start with some nice Gaussian process. Now, of course, if you now rescale the equation under the scaling up there, what's going to happen is that this guy is essentially going to be rescaled like white noise under the white noise rescaling. Of course, if I start with something Gaussian which has a nice covariance that integrates to 1, that covariance converges to a delta function. Okay, so it's exactly the delta scaling for the covariance. And so it's completely trivial that this guy converges to Edwards-Wilkinson under this rescaling. And so now so what kind of perturbation are we going to look at? Well, so the natural perturbation for these kind of models is, well, the kind of perturbation that Nicholas already mentioned, which is to have some, kind of function of the derivative, and we make it a perturbation, so we put a small parameter out in front. Okay, and well, the only reason why I put a square root epsilon is just so that I don't have epsilon squares in power 4 all over the place afterwards. Okay? So of course you can call this any way you want. And so now the conjecture is that, well, if you take a model like this and you scale it, you look at the correct scaling of this model, then you should be able to recover this KPZ equation. Now, of course, if you want the even more interesting conjecture is that if you scale out even more, then you should recover the KPZ fixed point. But of course, nobody has any clue on how to prove that. Okay? But then on the other hand, the KPZ equation, well, that we sort of know. Okay, we know that at least for a reasonably large class of observables, it coincides with the KPZ fixed point in terms of the behavior at large scale. So there's a good chance of showing that solutions to the KPZ equation converge to the KPZ fixed point when you zoom out. And so you at least have some sort of there's like there are two small parameters, and if you take the limit in the wrong order, you could recover the KPZ fixed point. Of course, you'd like to take the limit in the other order. And nobody knows how to do that. Okay, so, yes?
Is there a reason that the perturbation has to depend only on the x derivative of h, or could you have?
So, okay, so you could add a perturbation that depends on h also. It's not terribly natural, right? If you think of some sort of interface model like this, it's a stationary kind of interface model. Of course, one thing that you could imagine is that this f itself, for example, would be random, and that then it depends on h in a way which is kind of stationary in x translations and h translations now, right? So that would be a relatively natural thing to do, yeah, but we didn't look at that. Okay, so here we just take a deterministic, if you want, perturbation. Okay. So we have a number of results. So there's a theorem with Jeremy. So a theorem with Stell. So that goes back now to, I don't know, 15 or something. Which says that if f is polynomial, the natural thing here is to assume, right, so, I don't know, again, if you look at these kind of interface models, it's quite reasonable to assume that the model is invariant under just mapping x to minus x, right, that it's somehow invariant under horizontal reflections, and that corresponds to taking f even. Okay, so I'm always going to assume that f is even. If you add an odd part to f, it doesn't actually really change things, but what you end up with is you end up with some kind of a drift. And so in order to recover the KPZ equation, you have to actually make a change of coordinates also where you sort of follow you follow the average speed of the characteristics. Okay, so here we just assume that that's 0. It makes really not much of a difference. Okay, so we assume that f is even. So in the result with Jeremy, we showed that if f is a polynomial, then you have convergence to KPZ. And so the result I want to talk about today is actually a very recent, well, it's work in progress with Wei-Jun Zhu at Warwick. So I don't know, let's put 1718 to be on the safer side. So here we can basically drop the assumption that f is polynomial. We can take f somewhat arbitrary. We still need to take f just smooth and polynomial growth.
How smooth do you
C15.
mean?
So, yeah. So at the moment, it's something like C15, so we can just as well think of C infinity. And polynomial growth really means the first 15 derivatives grow polynomially. there's no bound on the power of that polynomial growth, right? So it can be any power, but it has to be a fixed power. So you're not allowed to take f of x equal to e to the x squared or so, right? So this is not allowed. You can take f of x equal cosine x. So you don't need any convexity or anything, right? So you can take a cosine here. That's not a problem. You can take, for example, right, so one very natural example is f of h equal to, well, f of u, say u is the derivative of h, equals to square root of 1 plus u squared. Okay, so you're allowed to take that, for example. You're not allowed to take f of u equal absolute value of u, for example. Okay, so this is not allowed. We don't know how to treat that. That would be kind of a nice example. Okay, so the 15 is partly a result of being lazy, right? So, of course, obviously you could optimize the 15, but I don't think we could do better than about 4 or so. Okay, so at some point you really hit the limits of the method, and you probably hit them somewhere around 4. So clearly it will definitely not be able to deal with this. And you're going to see already that, I mean, I give you a few indications of how the proofs work. I mean, you'll see that definitely you need already C3 for like the first steps in the proof. Okay, but something like this is perfectly nice. Now, the way it relates, so we've seen in Nicholas' talk, so there are a number of other results on this kind of universality of KPZ equation with a number of different methods. So they're essentially, at this stage, there are kind of 3 classes of methods, right? So there's, on the one hand, they're the exact solvable models. So you have a collection of 5 or 6 models that are exactly solvable, and then for these you can do calculations. And so you can show, so for those you can in particular show real universality, right? At least for some of them now. For TASEP you can show it completely fully, you can characterize everything. For any initial condition, anything, you can get the limit. And for some of these other models with other initial conditions, well, you can get the limit for some initial conditions or in some regimes, okay? Then there's the martingale approach that Nicholas just explained. And that works for a rather large class of models, provided that you have this structure. So you need essentially 2 things. You need to know the invariant measure of the model. You need that the model is Markovian. And you need to basically know, you need to sort of reasonably explicitly be able to decompose the generator into a sort of symmetric and antisymmetric part. But of course, if you know what the invariant measure is, then it's easy to do that. If you don't know what the invariant measure is, if you just have implicit characterization of the invariant measure, then typically you don't know how to do that, right? So there it's important to have this structure here. Whereas for the method that I'm going to present here, what's important is that, well, it's somewhat important that the model is given in a form that at least resembles this, in the sense that you're able to separate in a reasonably neat way the 3 mechanisms, which is somehow the noise, the smoothing, and the nonlinear, the asymmetry, if you want, or lateral growth mechanism. Okay, so you need to somewhat have these mechanisms separated quite cleanly. But then, on the other hand, we don't care about things being Markovian, right? I mean, here we didn't assume that this guy was white in time, so it's allowed to have non-trivial time correlations as well. And we don't need to know the invariant measure. Okay, so we don't, so in particular, if that guy is not white in time, there's absolutely no way of knowing what the invariant measure, or what the stationary measure of this guy is. And even if this one is white in time, you actually know the invariant measure only if it's in a very specific form, in the sense that if that guy is some modifier convolved with white noise, then you have to also convolve that nonlinearity twice with the same modifier, and then it happens to have the kind of form for which you actually know what the invariant measure is. But as soon as you change this, you don't know what it is anymore, and then these methods break down. Okay, so this method here is sort of robust under not knowing what the invariant measure is, and therefore not having any sort of a priori control on the solutions on large scales. Okay. Yeah, so just let me just write down what descaling is, of course. So the scaling under which this converges here is really, you look at square root of epsilon h of x over epsilon, t over epsilon square, and then you have to subtract the average speed. And so the statement is always, there exists a choice of these constants c epsilon, so that if you do this rescaling, you converge to the KPZ equation. Of course, here things are already normalized in such a way that the Laplacian picks up a constant 1 in front. The noise is always white with the delta covariance. No, so here the scaling is really sort of the Edwards-Wilkinson scale. Because you see, you have to kind of, there's no laser pointer. Well, okay, let me just move that around. I can move it like that. You see, you can sort of need to move from here to here. And so here you're kind of in the regime of the Edwards-Wilkinson scaling.
Okay.
Right? So that's why it's really the 1, 2, 4 and not 1, 2, 3. And right, and in all of these cases, one can actually, one can give explicit expressions for this constant. So of course, there's a dominant part. So this constant typically behaves like c over epsilon plus somehow c tilde, and you have essentially explicit expressions for both c and c tilde. Okay, and so here, if you have, so I think, so this 1 over 12 that shows up very often, or 1 over 24, depending on how you normalize things, doesn't really show up here because of the time correlation. So I think that seems to be somewhat special for Markovian models, so if you have sort of no time correlations. So if you have no time correlation, you see this 1 over 24 showing up. If you do have time correlations, it doesn't show up. Okay. But you do have order 1, but there are order 1 corrections here, and the order 1 corrections depend on, in a rather complicated way, on the covariance function of that guy and on the precise shape of that function f. And if you take a non-Gaussian noise here, okay, so if you take something non-Gaussian, which you just, but has sufficiently many moments and sufficiently rapid decay or good enough mixing, then you have the same sort of results. And then in general, you might also have a 1 over square root epsilon correction to the average speed. But that one depends on the third cumulants of the noise, and the third cumulants vanish for Gaussian noise. Yeah. Okay. Okay, so how do you go about analyzing this? So the first thing you do is...
Sorry, so the statement
yes.
is that expression there converges to the solution of the KPZ equation?
Yes, that's fine. So that there is a choice of this constant here, and the choice is always going to be of that form for suitable values of these constants here, which you can explicitly write in terms of everything.
What kind of convergence then?
So here it's convergence. Well, if you just rescale the thing, so it can only be a weak convergence. So it's weak convergence on finite time horizons. And yes, and all of these results are also in finite boxes. Okay, so you rescale by epsilon, so it means that the original guy, you put it in a box of size 1 over epsilon. And then you put, say, periodic boundary conditions.
And it's always periodic.
Well, okay, I mean, as Dikler's mentioned that we have this result with Mate, where you can do other boundary conditions, and then you have these boundary effects, where somehow the value of the derivative of the boundary gets also renormalized in a way depending on the covariance structure of the noise, actually. Right. So the first thing we do is, well, let me just write down the rescaled equation. Well, maybe I just modify this one. So when you rescale it, then this becomes, so let me write xi epsilon, and xi epsilon is epsilon to the minus 3/2 eta of this xo epsilon t over epsilon square. So that's just the white noise scaling. And this turns into a so here you pick up a square root epsilon, which comes from the square root epsilon. Well, it's sort of a square root epsilon divided by epsilon, but then it turns around because of the change of variable, and you end up with a 1 over epsilon out in front. Okay, so the equation that you end up for that guy is this equation here, minus c epsilon. Okay. And now, of course, you see that formally it seems rather clear that you converge to KPZ, because you say, well, if this is even, you write it, say, as an infinite polynomial, so there's a quadratic term in which the epsilon cancels out the epsilon exactly. There's a constant term, but the constant term can be canceled out by that guy. And then if you look at the quartic term, well, you end up with an epsilon out in front. Okay, and so it should disappear. But of course, on the other hand, you know that it shouldn't, because if you think of the original equation that we started with was this equation here, where we just added a root epsilon times f of derivative of the solution. And so for small epsilon, well, it's going to look more or less like the solution to that guy, but the solution to that guy has fluctuations of order 1, and its derivative has fluctuations of order 1. And therefore, the argument of the nonlinearity that we add is of order 1. There's no reason why we would only see what happens near the origin, right? So it's clear that if you just Taylor expand it around the origin and you keep the first term and throw away everything else, that's going to give you the wrong answer, okay? So it looks like here, at the formal level, it looks like fourth power and so on would disappear, but of course you kind of know a priori that they shouldn't. Okay? Of course, the reason is that this looks like it's small, but it's actually really of order 1, because in the limit, this is going to look like a Brownian motion, and so it's going to look more or less like an epsilon regularization of a Brownian motion, but an epsilon regularization of a Brownian motion has derivatives of order 1 over root epsilon. Okay? So this derivative is really of order 1 over root epsilon, and so the argument here is really of order 1, actually. Okay? And so in the convergence to the KPZ equation, here you end up with a, right? So the only thing which is not fixed by the scaling and by the assumptions is actually, I could put a constant in front of that guy, right? So let me write, say, mu here. Okay, and the value of mu, so let's try to guess what the value of mu should be. So the first guess was that it would just be the coefficient in front of the quadratic term when I Taylor expand f at the origin, but we already figured out that that should be wrong. That's not the correct guess. Okay? And so the next best guess, which is the correct one, is to say that, well, there's some sort of a local averaging that happens, right? Which is that, so this guy, the derivative of the solution, you'd expect it locally to behave like the derivative of the solution to the model without the nonlinearity, right? And the derivative of the solution to that model is just going to be some Gaussian, in the stationary regime, it's going to be some Gaussian with some variance, okay? And I can normalize it so that it's 1. Well, okay, there's no normalization left, but well, yes, there is, because it depends a bit on the shape of eta. Okay, so I can say I can change the shape of eta so that it's 1, but it doesn't really matter. So if the derivative of this guy in the stationary regime is normal with variance 1, that means, well, we expect this guy to locally look everywhere more or less like a normal with variance 1. And so then what we expect to see is maybe some sort of an average of the second derivative of this guy with respect to that normal with variance 1. Right? And that gives you the correct answer. Okay, so here, the correct value, in both cases, of course, the correct value of mu here is a half times the integral of f second of u, normal, say 0 c of du, where c is just the variance of the derivative of the stationary solution of that guy. Okay, so that gives us the correct answer. And so a natural thing to do.
You would expect it averaging because the fluctuations are much faster than.
Yes, that's right. Right, because this guy, it sort of renews itself on scales of order 1 at the microscopic scale. Right? And so at the macro, so by the time you've rescaled here, whenever you take points that are more than about epsilon apart, you already see things that are almost independent. Right? So the argument here fluctuates sort of really, really fast. It's of order 1, but it fluctuates really, really fast. And so it sort of self-averages. But then, because it self-averages, the average gets cancelled out by that constant. So then, of course, you see immediately that this constant here is just going to be the average of f according to exactly the same Gaussian measure. Okay? So that just cancels out the average. And then you only have these fluctuations that are left. But of course, these fluctuations, they are not going to be Gaussian. Okay, so it's not as if, right, because I claim that what you get in the limit is the KPZ equation. Whereas if these fluctuations were Gaussian, you would just get back to somehow stochastic heat equation with just an additional contribution to the noise. Somehow you would essentially just end up sort of slightly rescaling the variance of the noise or something like that. And that's not what happens. Okay. So what do we do? So we're going to, the first thing we do is we look at just the rescaled linear equation. So I write, say, x epsilon plus psi epsilon. Okay, so that's the equation where I've just removed the nonlinearity completely. And let me also call y epsilon square root epsilon times the derivative of x epsilon, because that's how it's going to show up in the nonlinearity. And then I can write h epsilon as x epsilon plus v epsilon. Okay, and then I can derive an equation for v. And so if you just plug it into this equation, what you get is this plus 1 over epsilon f of root epsilon dxv plus y epsilon. That's right, so the noise is cancelled out, and you just have the nonlinearity left, and, well, you just plug this in. And now you can guess that this quantity here should be small, okay? Because the hope is that once you've subtracted this, well, this encodes most of the local fluctuations of the derivative, okay? And then there's something left, but the thing that's left should be of low order, okay? So hopefully this is small. And so then you can Taylor expand this. Okay, so you can write this as 1 over epsilon f of y epsilon plus 1 over root epsilon f prime of y epsilon times dxv plus f sub 1/2 f second of y epsilon times dxv square, and then plus something small. Okay, and so there you have a good chance that you can a priori bound that remainder, or maybe in some sort of self-consistent way once you know what the limit is, and you can just forget about this. Okay, so this you can really basically just forget about it. And here you already see that we really need basically at least 3 derivatives for f, because we need to have a good bound on that remainder. And so now the hope, so what's the hope? Is that, well, so that 1 over epsilon f of y epsilon, well, minus a suitable constant, that this converges to, well, the limiting object, which should be something like a Wick square of, you know, the limit of this guy here. And similarly, 1 over root epsilon f prime of y epsilon, you would hope that it just converged to this guy, and that f second, well, 1/2 of f second of y epsilon just converges. Well, here there are constants, so there's this constant mu out in front, and this would expect it to just converge to mu. Maybe here you want a 2 or something. Okay, so if this were the case, then at least formally what you would see, if I simply replace these 3 guys by these quantities here, then at least formally I would simply see the KPZ equation, well, the equation that you get when you look at the solution to the KPZ equation, but you subtract the linearized part. Okay? So then you would somehow get the right equation, and then hopefully you would be able to show that these converge to each other. And so now there are 2 difficulties here. Okay, so the first one is that, well, it's relatively easy to see that this is true, okay, in the sense that it's relatively easy to see that if you look at the chaos expansion, so this, okay, so this guy is a space-time distribution. You can make sense of it as a space-time distribution. So here convergence has to be in a weak sense, not weak in the probabilistic sense, but weak in the PDE sense, in the sense that you first need to test against the test function, and then you get convergence. And this is then relatively easy to show. So it's quite easy to show that if you test that guy against the test function and you look at its chaos expansion, the term in the second chaos converges to a limit, and the limit is given by this guy, and the terms in every other chaos converge to 0. Okay, and same thing for these guys here. Okay, so here the term in the first chaos converges to a limit, which is the right limit, and here just the term in the 0 chaos converges to a limit, and everything else goes to 0. Now the problem is that this is an extremely weak notion of convergence, and this solution is in no way continuous in any topology in which you get these kind of convergence here. Okay, so that's one major problem here, is that actually what you end up seeing at the end is that even if, for example, if the limit, if you knew already exactly that the limit is KPZ equation, and if you look at the analog of this process V here for the KPZ equation, then for example, what you realize is that V itself is not differentiable. Right? So the solution to the KPZ equation locally looks like the solution to the stochastic heat equation, but the remainder is not, it has more regularity, but it's still not differentiable. So in particular, this guy itself actually behaves like log epsilon, as epsilon goes to 0. Okay, so even you can have any sort of convergence that you want for that guy, this product itself is not going to converge because that guy by itself actually diverges as epsilon goes to 0. And in the same way, this guy here, what actually ends up happening is that there are resonances between the fluctuations of this guy here and the fluctuations of this guy here. And these resonances cause that product to also diverge like log epsilon. And then actually what happens is that these two logs cancel out. Okay? But so you see that you would clearly have a problem if you want to just say, oh, well, I know this, and so I'm done. Right? Because you have to actually figure out that these two logs, that there are these two logs, and these two logs actually cancel out. Okay? And so this is the problem which is kind of solved by this theory of regularity structures, which in some sense you can view it as like a higher order version of this sort of expansion, right? Where you somehow expand your solution in terms of something which is known explicitly plus a remainder, except that then at some point you cannot do this expansion globally anymore. Okay, so here it's global in the sense that you say H, the whole process, is equal to this guy, which is also globally defined, plus a remainder. And at some point what you have to do is a similar sort of expansion, but where the terms in the expansion depend on the space-time point around which you perform the expansion. Okay, so the expansion actually becomes local rather than global. And then you can, well, if you perform this expansion to sufficiently high order, well, then you can make sort of your description of the solution or the candidate solution sufficiently precise so that it allows you to encode, for example, these sort of divergences and to see that they cancel out. Okay? So that's how you somehow solve that problem. And the other problem then is that, okay, so you have this kind of general theory that allows you to sort of deal with these sort of problems. But then what it does is it gives you some kind of big space which contains more than just these three guys. So it basically tells you have to not just control these three guys, but you have to control some higher order functionals of the noise, which now become some sort of multilinear functionals of these f prime and f second. And you actually have to show that these guys converge to some random variables that live in a higher order Wiener chaos. Okay, so this guy was in the second chaos, this was in the first chaos, this guy was in the zeroth chaos. Well, there are additional random variables living in the third and the fourth chaos, where you actually have to show that, the correct kind of multilinear expressions of these guys messed about with the heat kernel converge to the correct random variable living in the third and fourth Wiener chaos. And furthermore, this convergence needs to take place in some very, very strong topology. So you need some extremely fine control. So it's not enough to just say, oh, I know that every component separately in the Wiener chaos converges to 0, because what happens is if you naively somehow try to control this, you start to get relatively poor control on what happens in the higher order Wiener chaoses. And so, for example, you get relatively poor control on convergence of high moments, and that then translates into relatively poor control on the topology in which the convergence takes place. And you need some, in order to be able to apply this regularity structure business, well, one disadvantage is that, well, you need control in some very, very, very strong norms. Okay, so they are actually extremely close to the optimal norms in which you would expect the convergence to take place. Right? So in the sense that this guy here can certainly not converge to this constant in L infinity, because we know that this has fluctuations of size 1. Okay? But then, so it can only converge in some weak sense. And then what you want is you want it to converge in a negative Hölder space with arbitrarily small negative exponents. So it's somehow almost as close to L infinity as you could possibly realistically get. It's like the closest space to L infinity, which is not L infinity somehow. Right? And a similar thing then happens with all these higher order terms. You need convergence in extremely strong topologies. And so okay, I think I should kind of stop here. So let me just say 2 words about the tricks that we use. So one trick that we use is that we actually then end up Fourier expanding. So it turns out to be very advantageous to Fourier expand f, okay, to rewrite f as a, in its Fourier representation. And then you end up having to control expressions. You have to have sort of very precise control on things like sort of trigonometric polynomials of these y epsilons evaluated at different space-time points. Right? So you need to get good control on these kind of expressions with k in front here, right? And in particular, you need good control as k goes to infinity, and that's in order to be able to deal with just smooth functions rather than having to assume that it's entire functions or something like this. Okay, you don't want to assume entire functions, like square root of 1 plus u squared is not an entire function. So if you want to be able to deal with smooth functions, you need like polynomial control on these kind of expressions as k goes to infinity. And the thing that you would typically get is exponential control, or even like control that goes like e to the k square. And then the trick that we use is that so you have point configurations in space-time for which you want to control these type of expressions. And what you start to see is that you have problems when some of these points are very close to each other. And so then what you do is that you group your points into clusters, and you take clusters here of diameter about k square epsilon. And then for points within the cluster, you use explicit trigonometric identities, right? So you know that the product of cosines, you can rewrite it as a cosine of a sum, or sine of a sum. Okay? And so then that allows to encode cancellations, actually, that happen in these covariances. And so you group these points into these clusters. Within a cluster, you exploit explicit trigonometric identities. And then you have a product of cosines, but with maybe less factors. And then you actually perform chaos expansions of these. Okay, but it's important to actually do this. That's why we have to go into this Fourier space, is that then we have these exact identities that allow us to do this sort of clustering. And we have to do this before then performing a chaos expansion. And that allows to sort of encode cancellations of the coefficients in the chaos expansions, which then gives us a good control, which ends up being polynomial in k. And otherwise, we would only have control that's exponential in k, which wouldn't allow us to get sort of nice examples like square root of 1 plus u squared. Okay, so I can stop here. And thank you very much for your attention.
Thank you very much. Questions? If somebody wants to ask questions, I expect this. Then please use microphone. Yes.
So in the special case where capital F is a polynomial, do you essentially follow the same approach, or is there one point with
yeah, so in the case where f is a polynomial, so here, for example, we don't even do that. If it's a polynomial, it has a finite sort of Taylor expansion, right? So we directly, the whole thing is a polynomial. You can sort of directly fit this into this theory of regularity structures. And then when these things are polynomial, then they already have a finite chaos expansion. So you don't have all of these problems of sort of controlling what happens in the higher order chaoses, right? Because it stops at a finite order. And so that makes it much easier sort of from both points of view.
Other questions? Thank you.